Hey, you guys are there.
We are.
Yeah, we're
Oh,
here.
good. Oh, good
Except we're
evening.
not here.
Yeah,
We're not there.
it's
all right.
another virtual telescope viewing.
Yeah, yeah,
Yeah,
yeah.
Unfortunately.
I was just thinking there's really nothing worse than looking outside and seeing that it's, reasonably clear, and then also realizing that the humidity is above 85%.
Yeah,
Yeah,
when we were
and it's very windy up there as well. So
when we were up there, when we were still able to have people over there, that always became a hard question to respond to. It's so clear out. Why aren't you open?
Well, and it's even harder when they're lined up right at the telescope, right?
Yes.
It's
yeah,
like, yeah,
yeah.
at least we've got a little distance here. We could, get away with it a little easier. Anyway, thank you all for
Well,
joining us tonight, and I want to thank our sponsors for the Fremont Bank for supporting Chabot and supporting this program and others. And want to remind people that we count on your donations to continue these virtual programs and to help us prepare for the reopening of the Science Center, which, knock on wood, will be in very soon in the coming few months, and hopefully early summer. Um, and if you're interested in donating, look for the funny looking orange button at the bottom of your screen. It looks like a coin with a heart on it. And that will allow you to do a
is
donation.
that on Facebook or?
Yeah, that's the Facebook
And then
donation.
I don't believe there is one on the YouTube page,
There's
right?
not, no.
Yeah. Yeah, okay.
So if you are on YouTube and you would like to make a donation, visit the website for Chabot at chabotspace.org, and there's a place to do it there.
All right.
Well, we do have a good program for you tonight. It just doesn't involve live telescope viewing. So,
Hey, Rich, we should
yeah.
start by following up on something that happened last night during our virtual program
Ah, yes.
last
Okay.
last night.
It's
So,
all yours, Gerald. You've got.
so, some of the audience tonight may have been watching last night. We did a program called "The Sky This Month," and we showed a video that talked about all the different constellations that are in the sky during the month of February. And there was a major faux pas in that video, a misidentification of a couple of constellations. So I wanted to clear that up tonight, just for anybody who was there last night and is still wondering. Let me just go quickly to a couple of PowerPoint slides here, and we'll get it straightened out here. So this is similar to what we showed last night. The constellation Orion here, and during the video he talked about Orion and the belt of Orion and so on, and then he talked about Orion's two dogs, and he talked about this constellation and that constellation, and he incorrectly identified them as Ursa Major and Ursa Minor. In fact, those two are Canis Major and Canis Minor.
Dogs,
Right?
not bears.
Dogs, not
Right.
bears.
Yeah.
The canis part refers to dogs, not bears. So,
If your dog is an Ursa, you've got big
so,
problems.
That's a big dog.
Yeah,
later
yeah.
on last night, I gave Don Saito, who's the producer and narrator of that video, I gave him a really hard time about getting his majors and minors mixed up. So again, the two dog constellations near Orion are Canis Major and Canis Minor. The bright stars are Sirius and Procyon. And just to further clarify here, this is where the bears are in the northern sky. Orion and the dogs are in the southern sky. In the northern sky, we have Ursa Major and we have Ursa Minor, the bears. So we got Big Bear and Little Bear in the northern sky, and Big Dog and Little Dog in the southern sky. All right. So
Yeah.
that clears that up, and so we're
Well,
all
we forgive Don. He's a good guy, and
yeah,
I have certainly made worse mistakes.
yeah, really.
That is for
And
sure.
I told Don that I'm keeping that video in my new Don Saito blooper collection. So all right. Well, I guess tonight, if we were on the observatory, or we would have the camera on the telescope, and we would be looking, probably one of the first things we'd look at is the Great Orion Nebula. So this is what it looks like. These are images that you took, right,
Yeah,
Richard?
this is from the stack from a few weeks ago. Uh, the, about a couple dozen images stacked.
Right, right. So last week we were showing this image, and we were talking about these four stars right here. Actually, I guess you have to
Yeah,
circle them.
I
There
have
you
to
go.
do that.
Yeah, those four stars we call the trapezium stars. They're very young, very hot stars that formed out of this cloud of gas and dust, and they are relatively new to what we call the main sequence. So I'm Don, or Richard, if you can talk for just a second about those while I get my slides straightened out here.
Yeah, so go ahead.
Yeah, before
Yeah,
you do,
actually, yeah, we had a question that I think deserves
Okay,
answering.
yeah,
Are you
yeah,
able to
yeah,
go
get that?
ahead, go
Yeah.
ahead,
I
yeah,
was just going
yeah.
to mention that.
I'll get this
Go for it,
straightened
John.
out here.
So yeah, Nancy asked, how does the humidity impact your ability to see the stars?
Oh, yeah, good question.
Well, it's not so much that it bothers us seeing the stars. It could fog up the telescope a little bit, but that's the real reason is that the humidity will cause moisture to condense on the optics of the telescope, and it leaves dirt and dust behind, and that's really very bad for the telescope. So when the humidity gets above a certain point, we just don't open the telescopes. We keep them all closed up so that the moisture can't condense on the optics.
Right, right. You know, if you've ever had condensation on the front windshield of your car or on the window of your house, you know it's not so easy to see through it when you've got all that moisture on there. And same thing is true with telescopes. So anyway, I'm sort of ready now here.
Okay, go for it. Yeah.
So we talked about the trapezium. Go ahead and put that image back up for just a
Oh,
second, Richard. We
okay.
talked about the trapezium and those four stars. They're very young stars. They're very massive stars. So massive stars burn much hotter than stars like our sun. And so we mentioned that massive stars like those have very short lives. And some of the questions we got during that session was about, well, okay, what is a short life for a massive star versus for the sun? So I thought what I'd do is kind of go through and show you a little bit about that subject. Uh, Let me switch to my slide here. All right. And I think
Great.
there we go. Yeah.
Yep.
All right.
Got it.
Okay.
Mhm.
So when a star first forms out of a huge cloud of gas and dust, it condenses. At first, it's not fusing. It's not generating a lot of heat. But as it condenses, it gets hotter and hotter, and denser, and eventually the star turns on. We say it turns on. And when it turns on is when it starts to fuse hydrogen at its core. The star is composed mostly of hydrogen. And when it gets hot enough and dense enough at the core of the star, it begins fusion. And fusion means hydrogen atoms are being combined to form helium. So once the star has turned on and has settled down to where it's now just kind of routinely fusing hydrogen, we say it's a main sequence star. So after it turns on, it goes to the main sequence. It's fusing hydrogen at its core. It's in what we call hydrostatic equilibrium. That fusion process at the core generates outward pressure, which wants to expand the star. But because the star is so big and heavy and massive, that it has very strong gravity that wants to compress the star. And what happens when the star is on the main sequence is those two forces are in balance. So there's the outward pressure of the fusion being counteracted by the inward pressure of the gravitational pull of the star. So a main sequence star is the main lifespan of a normal star. The star spends most of its life on the main sequence. Up to 90% of its life is spent on the main sequence. And the lifetime of a star, the way we refer to a star's lifetime, is based on how long it spends on the main sequence. Because once it gets old enough to leave the main sequence, things start to happen fairly fast in star time. And so, it's the primary determination of its lifetime is how long does it stay on the main sequence. The greater the mass of the star, the shorter its lifetime. A star with a lot more mass is a lot hotter in its interior. It uses up its hydrogen fuel faster, and so it has a shorter lifetime. Now, the way that astronomers kind of track all this and classify stars according to where they are in the main sequence and where they are in their lifetime is using a diagram called the Hertzsprung-Russell diagram, which is sort of a graphic way of understanding how all that works. So I've got a Hertzsprung diagram here that I put together during the week just to kind of illustrate this point. When a star is first turns on and settles down, it goes on to the main sequence. And where it is on the main sequence depends on its mass. So a star that's very low mass is going to be down in this part of the main sequence. A star that's very high mass is going to be up here. Now, the way we kind of measure things on the Hertzsprung-Russell diagram is based on the sun. We use the sun as a unit of measure, if you will. The sun's luminosity, how much light and energy it gives off, we call that a luminosity of 1. And the sun's mass we call 1 solar mass. So this is where the sun is on the Hertzsprung-Russell diagram. It's on the main sequence right now, and its temperature is about 5,800 Kelvin, and of course it's 1 solar mass. All right. Now, most stars in the night sky are actually lower mass than our sun. And we'll talk a little bit more about that in a second, why that is. But you have a lot more stars out there that are maybe a 7/10 of a solar mass or 3/10 of a solar mass, or even less. It can be actually less than 1/10 of a solar mass and still be a fusing star. And then there are fewer stars that are larger than the sun, more mass than the sun, stars that are twice the solar mass, 3 times the solar mass, 10 times the solar mass. You get stars up here that are 30, 40, 50, 100 times a solar mass. A star can be easily 100 times solar mass. More massive stars burn hotter, and they don't stay on the main sequence as long. Okay, so we measure the luminosity. Here's a measure of the luminosity, and you see that a star that's maybe 3 solar masses, it's going to be 60, 70, 80 times the luminosity of the sun. And this is when it's on the main sequence. Star 10 times the solar mass is going to be somewhere around 3,700, 4,000 or so times the solar mass. The scales that you see here are logarithmic. So we go from 1 to 100 to 10,000 to 1,000,000 and so on. And that's because if we try to draw this in a linear scale where we went from 1 to 2 to 3 to 4 and so on, it would have to be a huge diagram. So
you need a larger monitor.
Right.
Wouldn't fit on your phones.
Right. So stars stay for some period of time on the main sequence, and how long they stay on the main sequence depends on the star's mass. Now, once the star reaches the end of its life, it leaves the main sequence. Initially, it goes up above the main sequence, and it goes through some gyrations as the hydrogen fusion at the core stops and starts fusing helium and so forth. Eventually, the star gets very large in diameter. It becomes a giant star, and if it's massive enough, it becomes a supergiant star. Uh, and then eventually, it blows off its outer layers, and most stars then become white dwarfs. So this is sort of the stellar graveyard, if you will. White dwarfs, that's where they all end. But that last part, going off the main sequence and going up into the giant phase and then eventually the white dwarf phase, the time it takes to do that is very short compared to the total time that it spends on the main sequence.
But the amount of time it might spend as a white dwarf can be very, very long.
Trillions of years.
Yeah.
Right.
I mean, that's like the most stable configuration of a
Right.
star.
Eventually, the white dwarf, which is very small, it's maybe the diameter of the Earth, maybe 10,000, 8,000, 10,000 miles in diameter, but it's got all of the remaining heat from that star before it collapsed into a white dwarf. And it takes billions and billions of years to lose that heat. Eventually, it will lose it, and the white dwarf becomes a what we call a black dwarf, which is just this cold, dead, dark lump of matter out in space. It's a very dense type of matter called degenerate matter, and that's the end game. But it takes, in many cases, trillions of years to get to that point. So, not too many black dwarfs out there because that's just more time than we've been around. So
Yeah, we only have 13 and a half billion
13 and a
years
half
of
billion
data.
years. Right,
Yeah, yeah.
right,
So
right.
it's
So
kind of tough. We're assuming that that's what it would be based on our observation of the energy that's given out by these stars. I have a question. Would you say that all stars start their life on the main sequence, or are there exceptions to that?
I'm pretty sure that most of them, possibly there are some exceptions in the very early part of the universe, but today all stars settle onto the main sequence for some period of time. Um, they start out actually on the main sequence, what we call zero age main sequence or ZAMS. Um, and then they wander around. They actually will slowly migrate above it, and then eventually they very quickly leave the main sequence. So,
Huh.
Yeah, that corresponds with a question on Facebook here. Jasper asks, also, how do we discuss lifetimes of stars that are never on the main sequence, like the Pistol star? I'm not
Well,
aware
the
of that.
pistol star is a blue giant. It's a very
Okay.
yeah,
hot giant
yeah,
star. But when it first fired up, it would have been way up on the top of the main
right up
sequence.
here. Yeah, right up
Yeah,
here. Yeah.
Yeah. Okay.
And it would not have been there very long. In fact,
right.
to kind of illustrate that point, I've got another graph to show you here. There's actually an equation that we use to roughly estimate for a given stellar mass when it starts on the main sequence, how long will it stay on the main sequence? And because that's 90% of its life, you're giving a pretty good estimate of what the star's total lifespan is. So I went ahead and took that equation and crunched the numbers for a few different masses, and here's the result. So down here we see one solar mass. So this is the sun. It has one sun lifetime. And for our sun, that lifetime on the main sequence is going to be roughly 10 million years or 10
Billion.
billion years. Thank you.
Yeah.
Maybe a little bit more than that. Right. So using the sun's mass as a unit of one and the sun's lifetime as a unit of one, you then work this equation to come up with what's the lifetime of a star in solar lifetimes based on the mass of the star. So if a star has twice the sun's mass, its lifetime will be 0.17 of what the sun's lifetime is. So that equates to 1,767,760 or
77 million.
767 million. I'll get it right. Yeah. So much shorter, double the mass, and you get a much shorter lifetime here. Not a little over 1/10 the lifetime. You go 5 times the solar mass, and now you've got a star that only lasts about 0.018 solar life spans, which is 178,885,000 years. And again, these are all rough numbers. They're not precise. They're ballpark figures. They're maybe a little better than ballpark, but not much.
They look pretty precise with all those significant digits there.
Yeah.
Well, guilty as charged. And so,
Hey, Lynn asks a interesting question here. Does degenerate matter ever contribute to dark energy? Not sure.
Well, we don't know. We don't know what dark energy is.
We don't know yet.
It might contribute to dark matter.
Yeah, but we don't know.
If it ever goes through a phase of becoming non-baryonic matter, it might.
Yeah,
but
well,
dark energy, we just don't know enough about.
Degenerate matter is not the same as non-baryonic matter.
Right.
Degenerate matter is just, it's so highly compressed that normal physics that we associate with, things like expanding gas. If you heat gas, you expand it. With degenerate matter, that doesn't happen, and things like that. So it's
no. I wasn't saying it was non-baryonic. I was saying, is there a further phase where it might contribute to non-baryonic matter? Who knows?
So what I wanted to call your attention to, if you get up here to where you're like 25 solar masses or 40 or 50 solar masses, you see that the lifespan on the main sequence becomes a lot shorter. At 25 solar masses, only 3 million years on the main sequence versus 10 million for a 1 solar mass. And you see down here, 0.8 solar mass, 17 billion years. So a star that was born early in the universe at 0.8 solar masses, it's still there. The universe has only been around for 13.8 billion years. So those very old stars are still around if they have less than 1 solar mass. But up here, this is where those trapezium stars are. Getting back to what we were talking about originally, those 4 stars are all stars that are in the 10 to 30 solar mass range. And because of that, they're not going to live more than maybe 3 or 4 million years. And all 4 of them recently landed on the main sequence. So they are in the main sequence, but they're not going to be there very long. And so for example, I think the most massive of the 4 stars is around 35 solar masses. And so it's going to survive maybe 1 million years on the main sequence, and then it's gone. And so, being big and massive sounds good, but it's actually not good for if you want to live a long time as a star. All right. So hopefully this all makes some sense to you. And, if not, shoot us some questions and we'll try to explain it.
Here's a good question.
I'm sorry. Go ahead.
Oh, I'm sorry. Go ahead. I'll go ahead. Margot or Little V wants to know, I guess, how long does a supernova last? And actually, that's a very short time.
Yeah, a few weeks.
Yeah.
Yeah. The initial explosion of a supernova just takes actually just a few hours to happen, and it ramps up in brightness very quickly. But then it slowly fades out over a period of several weeks, in some cases several months, and it depends on the type of supernova as well. But most stars don't die in a supernova. Most stars die in a very slow process where they swell up, they become giant stars, they lose their outer layers, the star collapses, becomes a white dwarf. It's surrounded by all that gas that it was expelling while it was a giant, and that produces what we call a planetary nebula. And then this is all a process that takes tens or even hundreds of thousands of years. So it's a much slower process. Only about 8 or 9% of all stars die in a supernova explosion. And those are the ones that are up here on the higher end of the mass range, solar masses or above. Those are the ones that can die in a supernova.
Maria asked a good question: is Betelgeuse in the main sequence? Not anymore.
Not anymore. Betelgeuse is
Right.
definitely in the
if you
supergiant.
go back a slide, and
Oh yeah, let's see if I can do that. There you go.
yeah, so Betelgeuse will be up where the red giants or the
Right
super
there.
giants are
Yeah,
actually. Yeah.
that's about right about where Betelgeuse is
Yeah.
right now, and it's actually working its way along this way, because as it loses matter, it gets brighter, and so and it gets hotter because you're exposing hotter interior. So it kind of works its way along here for a while, and then eventually the fusion stops. Whatever's left of the star collapses into a white dwarf and ends up down here. Although
Jerry said that that
Betelgeuse, it's
description
going
is
to blow up.
Jerry said that description is just like us.
Yeah.
Are you calling me a white dwarf?
Probably refers to the fact that as you get old, you swell up. You know.
Yeah, that's probably what he's referring to.
Betelgeuse will not become a white dwarf. Betelgeuse is actually so massive that it's going to explode as a supernova.
That's right. Cool. Do you want to tie this back to the picture of the Orion Nebula to look at some of the star types on that? Let me put that back up because
I'm not sure if I can identify which one is which.
Let's see if we can make some sense of that though, because brings it kind of full circle here. Because you do see various different types of stars in here, and with the the very bright ones and the trapeziums, which are very early stars, right, which will be in the upper part of the main sequence. Probably.
Right. One of these stars, probably the one you're pointing at right now, is a type O type star. We classify stars depending on where they are in temperature wise by a system called OBAF
KMN.
KM and so on. Yeah. And I won't do the mnemonic that we all learned.
So that's what I was doing in my head.
So anyway, the hottest of the stars is a type O star, and one of the 4 stars is a type O star. And that's probably the one you've got your cursor on, right?
Yeah, I think so.
And then the other 3 are all type B stars. One's a type B0, B1, and B1.5. Which ones are which, I don't know off the top of my head. But those are all a little bit cooler. They are still extremely hot, but they're a little bit cooler. When we say B0, B1, B1.5, within the classification we call stellar classification B, there's actually a range. And so the number after the letter corresponds to where it is in the range. 0 is the hottest and 9 would be the coolest. Within that range.
And you can see the incredible contrast just through sheer size and brightness with these much dimmer, smaller stars,
right.
smattering the whole the photograph, which are much further down on the HR diagram.
Well, plus you had to dim some of the trapezium stars down a little bit.
Oh, I did.
For this photo, right?
Right.
Yes.
Yeah, one of the things I talked about last night is how dim our sun would appear if it was, say, 50 or 60 light years away. And there's actually a star in the constellation Gemini.
Oh, this is great. This answers a question that goes way back in the early list here.
Okay. So
go for it.
There's a star in the constellation Gemini called 37 Geminorum, and it's almost a twin to our sun. It's 56 light years away, I think it is, somewhere in that range. And in this picture, it would be about as bright as the star that you see. There's the three stars that everybody thinks is the belt stars, and then there's a kind of a bright star below that. Those, nope, nope,
That one? This one?
that one right there. That's
All right.
about how bright it would appear uh, in a telescope. It's so dim that you really can't make it out with the naked eye unless you're in a very dark location, perfect seeing conditions. Uh, so our sun is definitely not one of the more massive, brighter stars in the night sky. It's a relatively dim star.
And that's a good thing because
Yeah,
Yes,
it
it'll
is.
yeah, we
last
like that.
longer.
It'll last longer, and it made it possible for Earth to be habitable.
Yeah.
Yep.
So somebody asked if we have found any black dwarfs yet. No, you can't see them, so we haven't found them. So, but there are probably some out there, but because they aren't emitting very much energy and because they're black in color, they would be very hard to find. But I suspect if one happened to drift by another star, we might see that other star wink out for just a second. So who knows? Maybe we have seen one and just didn't realize what it was we were seeing.
Well, they've got to be extremely rare if it
Yeah,
takes that
yeah.
long for a white
Right,
dwarf to cool
right,
down.
right,
No.
right. All right. So what else do we need to talk about tonight?
Well, we have a question that went way back. Let me see if I can find it again about alignment of planets. And I think this was just a misinterpretation of an app here. Here it is. So are the Sun, Jupiter, Venus, Saturn, Pluto, and the Moon in a line right now? I thought I saw that from my cell sky map. I think what he might have seen is a line depicting the ecliptic, and those are all on the ecliptic, obviously.
Yeah, that's right. Yeah, because they're
not
all
lined up right now.
No, they're not. No. Although, no, not really. They're all in the same line, what we call the ecliptic. The ecliptic is the plane of the Earth's orbit, and all of the other planets in the solar system orbit parallel to the Earth, more or less on the same plane. So they all seem to, march along a line across the sky, which is the extension of the Earth's orbit and what we call the ecliptic. Pluto orbits about it's tilted about 14 degrees to the ecliptic, but it sometimes is on the ecliptic and sometimes it's a little bit higher low of the ecliptic.
Yeah, he mentions a cell sky map. So very often these apps show the ecliptic as a line, and that's probably what.
That line's the ecliptic line. It's an imaginary line across the sky. Looking at YouTube here, May says she's in the middle of a snowstorm in Oklahoma. So you're not seeing any stars tonight.
Hey, I want to show you something.
Okay.
Our very own Rick Taft just sent me a photograph of the Orion Nebula by email that he had just finished processing, and it's a much larger field of view than what we're dealing with Nellie. And I thought people might enjoy seeing this since we're talking about Orion. Hold on, here we go. I got to make sure I bring up the right one here. There we go.
Oh yeah. Oh man.
That's quite beautiful. So the area that we were looking at in the last photograph is like right around here.
Yeah.
And just this little tiny spot is what we were talking about earlier. This gives you an idea just how large a nebula the M42 is.
It also does a great job of showing how the trapezium stars have created a pocket within the cloud.
Yeah.
Those stars, because they are so hot, so massive, they're putting out a tremendous amount of radiation, which actually pushes the cloud away from the stars. So that has already happened, creating that big pocket that you see.
Just like
just to the
whatever.
right of the trapezium.
Yeah, right
And
there.
so that's the
That little,
trapezium right there, and
and
then
then there's the pocket,
well,
right?
yeah, well,
And then
actually,
this
that
whole
that whole
area.
thing, yeah,
Yeah,
that whole thing is this pocket within this cloud.
I see.
So yeah, this is a much wider field of view,
Nice job.
and a lot more processing
Yeah.
and long
Rick,
exposure.
post how many hours exposure time
Yeah,
this was.
Yeah, and processing. I bet you he
Yeah.
took some time
Well,
with that.
yeah, processing times as much as exposure time, usually longer.
Here's a question. Jupiter. Was Jupiter far from becoming a star? In a word, yes.
yeah, it would have to accumulate a
Needed a
lot
lot
more
more
mass.
mass.
Yeah.
Okay.
All right. Rich, you had sent me an
Oh yeah.
image earlier today, I think
Yeah,
it
let me
was.
bring that up. See if I can here.
I've got it if you don't have it, I think.
Try again here. Here we go. Yeah, I will share. Here we go. This is from an artist. She describes herself as kind of a science graphics artist, and she has her name is Eleanor Lutz, and lives on the East Coast. And this is one of her latest graphic images. And what it is all of the known solar system objects, in which there are thousands of
Wow.
them known. And not only are they classified by color to some extent, but you notice how each one is almost like a little line, and that is probably the
Yeah,
known orbital element.
she showed the orbits
Yeah,
over a 40-year period for
yeah. Let me
the
see if I can.
asteroids, and
This is great. Gerald, how many planets are there in the solar system?
Yeah,
yeah,
exactly.
this actually illustrates the point. One of the things she did here is she didn't get all of the known objects. She got 18,000 of the known asteroids
Ah,
larger than a certain size, I think it was.
I see.
So
I see.
most of the
Thanks.
dots that you see actually represent asteroids. And what it does is it illustrates different asteroid regions, accumulations of asteroids around the solar system. Um, one thing that we should point out, this image is not to scale.
Right.
What she did is used a logarithmic scale so that
And you can see that if you look at the horizontal line, and there are these little divisions.
Yeah.
And they get
Right.
tighter and tighter and tighter as you go farther out. So this is actually really far away.
Right. So if you look, there's kind of a bluish green donut, if you will, about halfway between the center and the outside. Richard, if you can kind of point that out, that's the main asteroid belt. So that's where all those asteroids are that orbit the sun between Mars and Jupiter. And then on just above it, you see kind of a pink arc right there. That's what we call the Greek asteroids. And then if you go about down to the 5 o'clock, 4:30, 5 o'clock position, you see another kind of yellowish arc right there. That is the Trojans. And we actually
talked about that last week.
Yeah, some people use Trojans, call both groups of asteroids Trojans. Technically, the one that's lagging Jupiter is the Trojans, and the ones in front of it are the Greeks. But those identify those two regions there, and again, those are where the gravity of Jupiter and the gravity of the sun kind of are in balance, and asteroids tend to congregate in that region. And they're 60 degrees in front of Jupiter and 60 degrees behind Jupiter.
And this is where you spend all your time.
Yeah,
Near Earth asteroids.
Near Earth asteroids. And because so many of them are small, not very many of them showed up in her image here. And then you
That's
can't
good.
really, there's actually a lot of them out there. In fact, there are more than 18,000 near Earth asteroids. So, this is only showing the bigger asteroids. And then you've got some other types of asteroids out farther. You've got the Kuiper Belt. You've got what we call the scattered disk objects, the centaurs. Those are all just different groupings of asteroids and asteroid slash comet like bodies that surround the solar system. And you can't see it in this image here, but if you go to her website and zoom in, you can actually see the names of many of these objects.
Yeah, it's a really beautifully done. I mean, she sat there and moved, the individual text names around so they would match up with the objects. I mean, it was a lot of work.
Yeah,
So anyway,
It's
it's
amazing.
Eleanor Lutz, Lutz.com. I was also impressed with the all of the different products that she says. You can get this diagram on a comforter or a duvet cover or a mouse pad.
That's pretty cool.
And she does that for all of her graphics apparently.
Yeah.
So it's pretty
and
clever.
And if you're a real glutton for punishment, she will give you the source code so you can do your own version.
Oh yeah,
Wow.
that's right. That's right. Yeah, she does talk about how she got the data.
Yeah,
And this shows you a
yeah.
little
This
bit.
is a
This
closer
is a zoom in for the center
yeah.
of the solar system.
You don't
But
see it very
this
well,
talks
but she's
about-
named a bunch of them.
This talks about the data sources that she used. So
Yeah.
there's all this NASA, there's these NASA databases that are available, and then she cleans up the data, and then she uses Python to render the orbits based on the orbital elements in different colors based on their classification, and then using Illustrator and Photoshop, she goes ahead and puts the labels in one by one.
That's
And
amazing.
yeah, it's quite an amazing effort. And so anyway, she certainly deserves a lot of credit for doing this.
Yeah.
Oh,
Hey,
Rick
Rick-
got
oh.
back to us. Yeah,
I
sorry,
was just gonna say
John.
something.
I stole
That's
your
all right.
thunder there. He said that photograph is 2.4 hours of exposure time.
There you
So
go.
that's kind of a mid-range of exposure times for something like that, and it just kind of gives you an idea of how much time you have to spend aiming your telescope and camera at the sky to get a beautiful image like that. So.
Yep.
All right.
All right.
Let's
Well,
see.
how we doing on questions here?
Let's see. Got some more explanation from Rick on that image. He said it's a regular red, green, blue color image, but taken with an astronomical camera, which is more sensitive to the red wavelength, so it picks up that hydrogen gas. That's why that red was so obvious and profound in the image.
Yeah, somebody from Space TV said they'd like to see an animated version of Eleanor's graphic. Go to her website. You may be able to talk her into doing that. I'm sure she'd love to talk to you.
Yeah.
And she showed 18,000 asteroids. And like I say, there's actually millions of asteroids out there. And there are, she also shows the planets, and she shows that thing called Pluto, which, everybody wants to argue about whether it's a planet or not. And you heard John teasing me a little bit. My philosophy is Pluto is a planet. So are all those asteroids. So are the comets. There's all these different classifications. We have terrestrial planets, giant planets, dwarf planets, and minor planets. And when you add them all up, it comes out to millions. And so when kids ask me how many planets there are in the solar system, my response is there are millions of planets in the solar system. Forget this 8 or 9 or all that stuff. That's old school.
You're getting them into trouble at school.
Yes, I am. But I'm going to keep doing it until we get people up to speed here for the modern understanding of what the solar system looks
They'll
like.
answer that question and then have to explain it to the teacher.
Yeah.
Well, it is a good thing to do because really it's almost like a material science approach to the solar system,
I'm
right?
waiting.
You got hard things that go around the sun. They're planets,
Yeah,
you know.
yeah. There you go.
That's right.
I'm waiting for Neil deGrasse Tyson to come and visit us at the Chabot Space and Science Center, and he and I are going to go to war. All right.
He may be listening right now. Who knows?
Who
Never know.
knows?
We don't know who's listening.
Yeah. All right. How are we doing on questions here?
Still scanning here.
All right. Well, we wish we could be up at Chabot right now. Unfortunately, the weather is not being cooperative. The humidity has been bouncing around at our limit, and it is very windy up there too. We also
Yeah.
have a wind limit, and so we opted out for tonight. But I was looking at the long range forecast. Looks like we might get lucky next weekend,
Mhm.
and I'm really looking forward to that because we're coming up on galaxy season. As we get closer to springtime, we get into the part of the year where a lot of galaxies are in our night sky.
Leo and Virgo.
Yep,
Yep.
yep. Because of the orientation of the Earth's orbit around the sun, at different times of the year, we see different regions of the sky. And for much of the year, we're looking sort of into the galaxy, our own galaxy, or into huge clouds of gas and dust. And so we don't see very many galaxies. We see a few, but we don't see very many. But in the late winter and into the springtime, that's when the Earth gets in the right position in its orbit around the sun to where we are looking out away from the Milky Way galaxy out into deep space where all those other galaxies are. So when the weather starts cooperating again, we'll put a camera on Chabot's telescope and we'll start showing you some galaxies.
Got a couple questions, John. There's one on Facebook from Mark.
Oh. Have we been able to detect comets in the Oort cloud? Probably too far away to directly detect or image.
The Oort cloud is very far away, and so we don't image the Oort cloud very well. We know where it is. There have been some attempts to image it, not by actually imaging the object itself, but by watching for what we call occultations, where an Oort cloud object passes between us and a very distant star, and that distant star winks out for a second. And by timing when that happens, we can kind of estimate how far away that Oort cloud object is. But the Oort cloud is very far away, and it's completely surrounds the solar system. Unlike the Kuiper Belt, which is just kind of a torus that's close to the ecliptic, the Oort cloud completely surrounds the solar system. So you've got objects in the Oort cloud going every which way, and they're very far away. There are Oort cloud objects that are 1 light year away from the sun.
Yeah, if you remember that diagram from Eleanor, that it's a logarithmic scale, and the Oort cloud was way out at the edge.
Right.
So it's really far away.
One of the things we do is we measure distances in the solar system using what we call an astronomical unit. And an astronomical unit is the average distance between the Earth and the Sun. So it works out to be 92,955,807 miles, or 149,597,871 kilometers. Choose your unit of measure. So that is what we call an astronomical unit. So the Earth is average distance is 1 astronomical unit. The Mars's average distance is slightly over 1.5 astronomical units. Jupiter is 5.2 astronomical units, and so forth. So when you get out to the Kuiper Belt, we're beyond 30 astronomical units. Pluto, we now consider part of the Kuiper Belt. It's at 39.5 astronomical units. Um, the Oort cloud is much farther out there. The Oort cloud is 1,000 to 10,000 and maybe even 100,000 astronomical units. So it's a much huge region. There are a lot of objects out there. And a lot of the comets that we see once and never see again, they come from the Oort cloud.
Couple more questions. I'll take the first one and let you take the second one. A couple of people are asking about whether we'll be able to continue doing these live stream presentations after Chabot reopens. And the answer is we hope to.
Yeah.
There's been a lot of interest from the Science Center to have us continue doing this. It would be on different nights. In the normal universe, the Chabot Space and Science Center had live viewing from the telescopes open to the public on Friday and Saturday night. So if we were going to do something through live streaming, it would probably be midweek or on a different night, obviously, than the Friday and Saturday night. But yeah, the short answer is yes, we hope to do that. Then there's a question from Benoit. Is it true that the sun is a second generation star made from the remnants of a previous star? And I thought you would like to answer that.
Yes, yes. The sun is only 4.5 billion years old. In fact, to use a few extra significant figures, it's 4.567 billion years old.
I love that you have these numbers down so
Yeah. Well,
so accurately.
When you have to hammer them out so many times, they start settling in.
Harold has a good calculator.
So anyway, the galaxy itself is about 12 billion years old. So obviously the sun is much younger than our galaxy, and that means the sun was formed out of gas and dust, and a lot of that gas and dust was left over from earlier generations of stars. So the first generations of stars were likely low in what we call metals, but high in hydrogen and helium. They went through their lifespan. Eventually, they died either in a supernova or as a planetary nebula, which scattered gas and dust all over the universe. That recombined with other gas and dust to form yet more stars, and likely that our sun formed from a second generation gas and dust left over from that first generation of stars.
So is that why we have so many elements
right.
in our solar system?
Right. Yeah. When stars, as they age, they begin fusing. Initially, they're fusing hydrogen, then they fuse helium. They can eventually produce carbon and oxygen and neon and so on. And the more massive the star, the more elements they can form within the star. And so when they die, and especially if they explode, they throw all that stuff out there. And so that becomes part of the next generation of stars. So the first generation of stars is formed mostly from hydrogen and helium, but the next generation of stars has a lot of hydrogen and helium, but it's also got some of this other stuff that came from the first generation of stars. And so you get a lot of metals, silicon, you get oxygen and so on and so forth. All of the heavier elements are included, although the second generation star, or even the third generation star, they're still mostly hydrogen and helium, but they've got a little sprinkling of all this other heavier stuff. And so we say they are higher in metallicity. And that's one way we can identify what generation a star belongs to, is by how much of these other elements that we find within the star.
So we use spectroscopy
right
to look at stars and determine their metallicity. and we could distinguish the ones that are first generation from the ones that are second or third generation by seeing if there are spectral lines corresponding to those heavier elements. And that's how we know, for instance, that globular clusters contain really old stars
Right,
because they're
right.
low
Low
metallicity. And
metallicity,
so
right.
a lot of what we understand about stellar evolution and some of these exotic structures in the universe comes from figuring out this progression of star formation.
These guys at Space TV are having fun at our expense here. He says the Oort cloud is right next door. Yeah, right. Okay, if you say so.
You got a large neighborhood.
All right.
All right.
Any other questions or comments?
Yeah, now's the time.
Yeah, and again, just to reiterate what Richard was saying early on, the Chabot Space and Science Center, although it is closed to the public right now, we are still very active doing things like the virtual programming that you're watching now. We have other virtual programming that we do during the week, including daytime programming for schools. And we are refreshing much of the facility, working to develop new exhibits and so on. So we do continue to need your support, but since we are close to the public, we're not getting the revenue that we would normally get from, admissions and so forth. So we are relying a lot more right now on donations. So if you get a second, click that donate button or go to the Chabot website, chabotspace.org, click on the donate button there. And if you work for a company that likes to support nonprofit organizations, refer us to them. We'd love to hear from them. We encourage corporations like Fremont Bank to come in and help us out. Fremont Bank recently made a pretty generous donation to help us do a little bit of a refurbishment of our planetarium. So we encourage other corporations to do likewise.
And if you do donate, we do thank you very much.
Yes,
we really appreciate it.
We really do. Yeah. So how are we doing on questions here?
Barbara asks, well, what's the metallicity of the trapezium? Well, that would be second generation, right?
Right. Of course, they won't be around very long, and then they're going to.
Then they'll be third.
Then they'll contribute to the third generation.
More metals around for new generations of stars, right?
Yeah.
All right.
Very good.
All right. I think we've pretty well exhausted all the questions.
Yeah.
Comments.
Right.
Some good comments, but a lot.
So we'll be back again next week, and we have our fingers crossed that the weather's going to cooperate here, so we can put the camera on the telescope and show you some cool stuff. And in the meantime, if you've got any astronomical questions that you want to ask, be sure to write them down and have them ready for next week. The thing I really want to call your attention to is next Thursday.
Yeah, I was about to say. Good.
Yeah, next Thursday, the Perseverance rover with its Ingenuity helicopter attached to it is going to land on Mars. So that is going to occur. Their touchdown time right now is tentatively around 12:55 p.m. Pacific time. So just before 1 o'clock in the afternoon. The Chabot Space and Science Center is going to be live streaming that event with commentary starting at noontime. So if you go to our Facebook or YouTube page, you will see we will be carrying the NASA TV coverage. We will also have experts who will be answering your questions. You can submit questions just like you're doing tonight, and we will answer them, and we will kind of augment whatever commentary comes from NASA. And then at 1 o'clock or shortly thereafter, we are going to have two guests, two NASA engineers who worked on the development of the Ingenuity helicopter. That helicopter is a little helicopter that's riding underneath the belly of the rover. And after it lands and after they go through all the checkouts and everything, they're going to drop that helicopter onto the ground. The rover will move out of the way, and then the helicopter is going to take off and it's going to fly around. And it's going to do several flights around the rover on Mars. And this will be the first time that any type of vehicle has flown in the atmosphere of another planet. So something to really look forward to.
That should be a really interesting discussion.
So again, if you check in with us on our Facebook page or our YouTube page at noontime Pacific time on Thursday, February 18th, join us and we will cover that landing live and answer all your questions while we're doing it.
Sounds great.
All right.
All right. Well, thanks everyone, and you have a nice weekend, and we'll see you next time.
Happy Valentine's Day, everybody.
Oh yeah,
Thanks.
I forgot about that.